All right, today we're going to break down k-nearest neighbors, or KNN. And you know what? It's probably one of the most intuitive algorithms in all of machine learning. Seriously, it basically makes decisions the same way we do, by looking at the company we keep. So let's dive in and see how this surprisingly human approach actually works under the hood.
Okay, so let's start with this analogy because it is just perfect. Seriously, forget all the complex math for a second. At its absolute core, this whole algorithm is just about finding your tribe.
So let's stick with this cafeteria idea for a bit. How does KNN make decisions based on similarity? Well, the whole thing runs on a super simple principle. You are who your neighbors are. That's it. When it sees a new, unknown thing, it just looks at all the stuff it already knows, finds the ones that are most similar, and then basically lets them vote on what the new thing is. Okay, so here's the more textbook definition. Let's unpack a couple of these key terms. First, non-parametric. All that really means is that the algorithm doesn't make any assumptions about how the data is shaped. No assumptions about it being a straight line or a perfect curve. And then there's my favorite part, lazy learning. This is so important. KNN is kind of like the ultimate procrastinator of machine learning algorithms. It doesn't actually learn or build a model ahead of time. Nope. It just memorizes the entire training dataset and does all the heavy lifting right at the moment you ask for a prediction. All right, so how exactly do we measure who our neighbors are? This is the one piece of math you really need to know. Back to our digital cafeteria. How does the algorithm decide who's closest? It's not looking at their clothes or what music they like. It's doing something much simpler, actually. It's just measuring the mathematical distance between them.
And here it is. The most common way to do that is with something called Euclidean distance. I know, it sounds fancy, but it's really just the straight line distance between 2 points. As the crow flies. This little formula right here is the engine that drives the entire algorithm. And what's so cool is that it doesn't matter if you have 2 features or 200. This calculation just boils everything down to a single number that tells you how similar 2 things are. The smaller that number, the closer they are in the cafeteria. Simple as that.
Okay, theory is great and all, but let's get our hands dirty and see how this actually works in Python. We're going to do a quick 3-step proof of concept using the classic iris dataset. So, our mission, should we choose to accept it, is to teach a machine how to tell different species of iris flowers apart just by looking at the size of their petals and sepals. Let's do it. First things first, we've got to load our data. And if you take a look here, you can see what we're working with. We've got these 4 columns of measurements, sepal length, sepal width, and so on. These are our features. And then we have this final species column. That's our target. It's what we want our model to eventually learn how to predict.
Okay, now for step 1. And I cannot stress this enough. This step, feature scaling, is absolutely 100% mandatory for KNN. It's not optional. Think about it. What if one of our measurements was in millimeters and another was in kilometers? The distance calculation would be completely thrown off by the kilometers, right? It would just dominate everything. So we use something called standard scaler from Scikit-learn. It basically squishes and stretches all our features so they're on the same scale. It puts them on a level playing field so each one gets an equal vote in the distance calculation.
Step 2. And would you believe it? This is it. This one little line of code is the entire algorithm. We just call up k-nearest classifier from Scikit-learn and see that n neighbors equals 5. That's us telling the model, hey, when you need to classify a new flower, just go find the 5 closest flowers you've already met and ask them to vote. That number, 5, that's our k. And finally, step 3, train and predict. First, we fit the model. Now remember, because KNN is a lazy learner, fitting is a bit of a strong word. All we're really doing is showing it the training data and telling it to memorize everything. Then comes the fun part. We use predict to ask it to classify the new flowers it's never seen before. It's time to put our new flower in that digital cafeteria and see which table it sits at.
So, how did we do? To find out, we generate this classification report. This is awesome because it doesn't just give us one final score, it breaks down the performance for each type of flower. It tells us things like precision, which is basically, of all the times it guessed a certain species, how often was it right? And recall, which is, of all the flowers of that species that were actually there, how many did it manage to find?
And the final result? A whopping 98% accuracy. I mean, come on, that's pretty incredible. On a clean data set like this one, the simple logic of look at your neighbors gets us almost perfect results. It just goes to show how powerful this straightforward approach can really be.
Now, let's talk about the art of choosing K. This is what I like to call the Goldilocks problem of machine learning. We just randomly picked k equals 5 in our example, but was that really the best choice? This is probably the single most important decision you have to make when you're using KNN.
And it's all about this trade-off. See, if your k is too small, like say k equals 1, the model gets way too sensitive. It's listening to every single little noise and outlier. We call that overfitting. But if your k is too big, the model gets too broad and ignores all the important little details in the neighborhood. That's underfitting. We need to find that k that's just right. So how do we actually find that Goldilocks value? Well, a really common way is to try out a bunch of different k values and plot the error rate for each one. What you're looking for is this elbow point, right here. See how the error drops fast and then starts to flatten out? That spot, right at the bend of the elbow, is usually a pretty good bet for the best k value. To really hammer this home, let's visualize it. Let's actually see how the model's logic changes when we mess with the value of k.
Okay, look at this. When k is just 1, the boundaries between the classes are super complex and jagged. It's creating these weird little islands just to capture every single data point perfectly. This is a textbook sign of overfitting. The model hasn't learned the real pattern, it's just memorized the noise.
But now, check this out. We crank k up to 15 and boom! The boundary gets way smoother, much more generalized. This model is way more likely to do a good job on new data it's never seen before because it's captured the real, broad pattern instead of getting sidetracked by all the noisy little outliers. Okay, so after seeing all that, the big question is, when should you actually use KNN? When is it the right tool for the job? Let's break down the pros and cons. On the plus side, its biggest advantage is that it's just so simple and intuitive. You can actually explain to someone why it made the decision it did. And since it's a lazy learner with no real training time, it's an amazing model to start with. You can run it super fast to get a baseline for how well you should be doing before you move on to something way more complicated.
Now for the cons, and really they're the flip side of its lazy personality, because it has to compare a new point to every single point it's ever memorized, it can get incredibly slow when you have a huge data set. And for that same reason, it's a total memory hog, since it needs to keep that entire data set in memory.
But even with those downsides, you see the logic of KNN everywhere. I mean, every single time you see a recommendation like, customers who bought this also bought on a shopping site, that's the spirit of K-nearest neighbors right there. It's finding similar people to you. You also see it in things like image recognition, or even in medicine, finding patients who have similar symptoms.
And that's really it. That's K-nearest neighbors. It's simple, it's elegant, and it's a surprisingly powerful way to find patterns, all based on that one basic idea. You are defined by the company you keep. So now that you know how to find the nearest neighbor in any data set, what hidden groups could you uncover in your own world?
Like and subscribe for Simplify Tech, explaining one concept at a time, simplifying the technology and AI.